In this example, we're going to look at a power factor correction problem. This is the word problem that we've been given. And first step, as was in the last video that I made, was to take the word problem and draw it into a circuit. And then fill in all the values that you know and ask the question, right? We're looking for the capacitor, the capacitance of the capacitor that will give us a power factor correction of 0.9 lagging. Notice that I drew this with a dashed line. That's to remind myself that I first want to solve everything I can about the original circuit and then perform the power factor correction afterwards. So we'll begin with the step of drawing out the voltage and current on the complex plane. And we're not given an angle for the voltage, but we're going to choose the angle of the voltage. The voltage is our reference here, so it's going to be 0. And the current is lagging. So that means the current lags the voltage. And there isn't really too much that we need to do with this triangle. I just like to constantly remind myself that when current lags voltage, that the load is primarily inductive, and a primarily inductive load will have a positive reactance when you look at the complex power. So here's our complex power, also on a complex plane. Okay, and I happen to know already that this is 60 kilowatts, and I know that the angle theta is the same for both of these. And I could calculate that angle, right? Let's remind ourselves that the power factor is the cosine of the phase shift difference, or the phase difference between the voltage and the current. Okay, and so we know that in our initial conditions it's 0.075. Don't forget to use the 0, right? So this is the cosine, the inverse cosine of 0.75 will give us theta. And that angle is the inverse cosine, that's the green button here, inverse cosine of 0.75, 41.41. Okay, and it wasn't necessary to do for this first part, but it's important to remind yourself continually what this stuff is. We don't need to do it because I can solve for S without finding that angle. Remember that cosine is the adjacent over the hypotenuse. So if I want to find the hypotenuse, which is S1, S1 simply equals 60k over the cosine of theta. Well, we already know the cosine of theta. It's 0.75. So this is 60,000 over 0.75, which is equal to 80,000. Okay, and that's our magnitude. If we want to actually find the phasor, well, we already have that as well, right? That would be 80k at an angle of 41.41 degrees. And that is measured in volt amperes. We can also calculate the complex form of S. To calculate the complex form of S, I'll just use the TI-89 because that's the easiest way to do it. And I'm going to write this in phasor form. And then I would go to mode before I hit enter and make sure that my complex format is in rectangular. And of course, don't forget that your angles should be in degrees. Okay, so when I hit enter, it'll return me that same value, but in... Oops, I didn't enter it right, did I? The clue is that this should be 60,000, right? Because that's our real power. So this is supposed to be 4.1. Okay, so now it's 60,000. So it's 60K plus 52.9K and that's also in volt amperes. Okay, so now we filled in all of the missing pieces of our puzzle. And we're ready to move on to the power factor correction. So what I'm going to do first is I'm going to redraw that triangle really quickly so that it's a little bit bigger and easier to see. So this is S1. And this was 60 watts or 60 kilowatts. Okay, and we already had that angle theta in here. Now what we want to do is we want to bring the power factor to 0.9. So we want PF new equal to 0.9. To do that, we need to calculate what the angle would be, and we'll draw it in. So the power factor will be, and that's lagging too, right? So theoretically you could ask for leading, I guess, but I don't know why you do that. The cosine of 0.9, the inverse cosine, will give us theta new, and that angle is 25.84. So as you can see, the angle is less than what it originally was, like that. And that would in fact be S2. This angle is 25.84. Okay, so how are we going to achieve that? Well, we're going to have to reduce the reactive power that's absorbed in the circuit. And we'll do that by placing a capacitor in parallel with the circuit. Remember that capacitors supply reactive power, and when reactive power is supplied, power supplied is a negative sign, right? So it's going to in fact have the effect of pushing that original reactive power down. And kind of ran out of space here. This is going to be our reactive power of the capacitor, and we'll call this Q new for the new total or effective reactive power of our circuit. So we want to calculate Q new, and Q new is going to be a situation where we did need to calculate this angle, right? Because we're going to use the tangent of 25.84, which is not 0.9. We have the adjacent side, so that's going to be 60,000 times the tangent of 25.84. Plug that into your calculator and you will get 29056. Okay, that's Q new. And that value is positive, in fact, because this is what we're going to be left with, is this triangle. QC then is the difference between the original Q and Q new. So it's going to be 52.9K minus 29K, which equals 23858. Okay, and let's remember that that's negative, and these are both in vars. So we've now figured out the reactive power that the capacitor is going to supply, and we now need a way to relate that to its capacitance. We still can't answer this question yet. So how are we going to do that? Well, we'll probably need to start by relating the reactive power to the impedance. Remember that reactive power in general can be related to the current, and it could be related to the voltage. So that tells us then that Z equals V squared over Q. So that is, by the way, let's make sure we've got this completely explained here. V and I are the magnitudes of the respective values. So it's the magnitude of the voltage. And don't forget, complex power equals P plus JQ. I myself have made this mistake of sometimes equating Q with JQ, but Q is just Q. So when we're looking at this equation here, you don't want to put the J in there because it'll in fact give you a completely wrong sign answer, because when you have the J in here, it becomes a negative and the negatives cancel out, and that wouldn't make sense, right? Because we know that the impedance of a capacitor should be a negative value. So when you do this, 240, where am I getting 240 from? Well, the voltage across the capacitor is 240 volts. That's why I chose to use V squared over Z rather than I squared Z. Okay, so it's 240 squared over Q, which is minus 23858. Let's plug that into the calculator. 240 squared divided by negative 23858. And it returns the value in a in an exact format. If I want to make it not do that, I can push the green button here and then reevaluate. Okay, and so I get minus 2.41. Okay, and that's minus J, because that's what our impedance is. Okay, so remember that Z for a capacitor equals minus J times 1 over omega C. And so we get minus J 2.41 is equal to minus j times 1 over omega c. So I can cancel out the j's. If you divided them out, you just get positive 1. And switch this around here, and I'll get c equals 1 over omega times 2.41. Remember, our circuit here is a 60 hertz signal, and the frequency of 60 hertz is 377 times 2.41. Okay, and if you plug that into the calculator, 1 divided by 377 times 2.41, you will get 0.001101, which is the same as 1.1 microfarads. So I now have an answer to the question that I was originally asked, and my answer is 1.1 microfarads. Okay, and that's how you solve those kinds of questions. Good luck.